Yeah, perfect. Hi, welcome everyone to our Amygdala talk. Today we have Chandan with us, Chandan Yeshwanth. He's a PhD student in 3D AI lab at TUM Informatics department. And also before that, he completed his master's in robotics, cognition and control in from TUM. And he'll be talking about 3D AI about his research. So we are very grateful that Chandan is with us today, and it is up to you, Chandan.
Yeah, thanks for the introduction, Tata. It's my pleasure to be here and talk about my master's thesis work that I just completed a few months back, and then soon after started my PhD. This work was supervised by Professor Matthias Niesner, done at TUM. So let's get started. So I'll be giving some basic introduction to deep learning topics as well, and then later get into the actual problem itself. So some of you might be familiar with 2D semantic segmentation in deep learning, which is a well-explored problem. So here we have the input as RGB images, and we are looking to predict pixel label per pixel in the input. So this can be done for any kind of image, whether it's indoor scenes or say outdoor scenes, and any different kinds of classes, say indoor objects, or it could also be for surfaces like roads, vehicles, and so on. So a natural extension of this is to the 3D space when we have the 3D input data itself. So here, say the data is in the form of an input scene, which is a mesh here. And then we want to predict a label for each mesh vertex, which is each 3D location in the mesh, which could be something like this. This could also be done at different levels. It could be done per phase for different 3D locations. So we'll see what kind of variations there are in this. So here we can see the challenges are quite different once we move to 3D data, that a lot of it is just empty space, and then objects could be it's widely scattered and it might not be very complete. So based on how we got the mesh, so we need to look at what kind of data we actually have. Some applications of 3D semantic segmentation could be, say, for example, augmented reality, where a person wearing headset needs to recognize what objects are there around him, or in a self-driving car, similarly, to avoid obstacles and so on. So the means of capture of the data itself, there are many possibilities, but the task is quite similar finally when we're doing semantic segmentation. So one of the common data sets for semantic segmentation on indoor scenes, which is what I'll be talking about mostly, is the ScanNet benchmark, which has it is quite commonly used in many of the papers. There are some data sets that came later, such as Matterport and so on, but ScanNet is still quite relevant now. So the ScanNet data set has about 1,500 RGBD trajectories through scenes. We'll again see what a trajectory looks like. So then using these RGB trajectories, which is just 2D images and depth like shown here, it's possible to do a 3D reconstruction of the mesh like this, and this was done using an algorithm called bundle fusion, which would be interesting to look into in this field. And then once the mesh is obtained, the meshes were annotated mostly manually with some semi-automatic steps. And then the annotations themselves are in different forms. Say, for example, for different tasks such as object detection. Will you be admitting the people into the call here? Or should I do it? Okay, cool.
Yeah, I can take care of that. You don't need to worry.
Sure. I'm just seeing something here. So there is semantic segmentation and then there's instance segmentation. and so on. And this benchmark is set up for 20 classes, even though the data set itself has more than 20 classes. Right, so we can see that the reconstructions obtained here need not be very complete or very representative of the actual shapes and sizes of the images like what we would expect, but that makes it more challenging to identify what objects there are in the scene. So these are examples of the depth and RGB images that we would get from ScanNet. So a depth image is something that can be captured by, say, an iPad, or these days even with mobile phones and Kinect sensors, which represents the distance of every point in the image to the sensor from where it's being recorded. So right away we can see that the depth from these kind of sensors is quite noisy, and it could be quite far from the actual ground truth say shape of the image and locations. The RGB image is here on the right, which is a little more representative and something that we could understand ourselves. Right? So it's easy to make out what kind of objects there are in the image. These are examples of the camera trajectories in the ScanNet dataset. So we can see that, so this being the whole scene, these are the locations from which the RGB recordings are made. So this presents another challenge because it's possible that the cameras are not uniformly covering the scene. So you could have more coverage in some regions and then less in some regions, which gives rise to such holes in the reconstruction. So given this, we want to know what kind of representation we can use of the mesh to perform some kind of semantic understanding of the scene. So one of the common representations for 3D is voxel grid, which is one of the simplest representations, where the 3D space is divided into a regular grid of voxels like this, usually cubical voxels, and then every grid cell that is occupied in the mesh, say by a mesh vertex or a mesh face usually, is set to a 1, and then everything else is 0, that being the empty space. So if this is the original object, then at a certain resolution, say 32 cube, we are partitioning the, say, this space into a 32 cube, and then setting individual voxels to say 1 or 0. And then the space itself can be subdivided further. So based on the resolution of the voxel grid, you can get a more fine or coarse representation of the object as we increase the resolution. So again, it's apparent that the more we divide, it's better. It's more true to the original object. But at the same time, the space occupied in terms of storage and the computational requirements are going to increase cubically, right? So for each time we go, say we divide each of these voxels along each dimension into 2, that means the overall size of the voxel grid is increasing by 8 times. Right, so we can see there's a challenge, and then soon we are going to reach some point at which all of this is not going to fit into memory, and then we have to tackle that in different ways. So applying the same thing to our ScanNet scenes, we would get something like this at a certain resolution. So this is a 4 centimeter resolution voxel grid, and we can see that we lose out on a lot of detail here. While this is the sacrifice that has to be made to actually fit things into memory and make them computationally feasible. And this is at the same time, we are not using any color here. This is just the geometry of the objects. So having this kind of a representation of the scene, we want to see how we can do semantic segmentation on the scene. So this is the original mesh of the scene. So like I said, the voxel grid for the whole scene at say a 4 centimeter or a given resolution would be quite a lot. The grid would be huge. So we pick a certain area of the scene and make a subvolume from there, which will look something like this, a 3D subvolume. So these are just the extents of the subvolume that we are considering. And these are the actual voxels that are occupied inside this subvolume. And now we want to predict the labels for each of these voxels. So what we do is we take the subvolume and then apply a 3D convolution on this, which is possibly the simplest method that we can do here. So this is a 3D unit kind of downsampling and upsampling architecture, where we can get a predicted volume which has labels directly from the subvolume. So this is the one of the methods that was used in the original ScanNet paper and in this more recent paper called 3DMV. So this works, right? And then we want to see so we're not using all the data that is present in ScanNet when we do this. We are only using the 3D representation and not using the 2D or the depth images anymore. Right? So does it help to actually use the 2D information? So if we compare the RGB and the voxel grid for the same location, so here we can see the RGB has much higher resolution details, right? So in this image, we can actually make out things like the handles of the doors, the tap and the sink, then say the door of the fridge and so on. Whereas when we voxelize at a coarse resolution, we just get a coarse structure which could tell us that, say, this is a counter, this is a sink, right? This could possibly be a fridge based on where it's located and what its size is. But we can't really say more than that. So somehow we want to combine the information that is there in the RGB with the voxel grid at the appropriate location to see if that can help us improve the 3D performance. So this is exactly what was done in 3DMV, which is already a couple of years old now. So I'll explain what is actually done there. So we have we take this the voxel grid of a scene. And so we'll pick one subvolume from the voxel grid, which will look something like this. So in red, we highlighted the voxels that belong to this subvolume. So you can see in comparison to the whole scene, we have to pick quite a small region of a constant size to make things work. And the other thing to notice here is just for simplicity, we take the subvolumes that cover the whole height of the scene so that we don't have to move in all directions. So once we do this, because we know that for most of the indoor scenes, say the height of the scene is about 3 meters or so. So we wouldn't really need to have multiple subvolumes stacked on top of each other when we're considering the scene. And we'll have to only move in the X and Y axis when we do this. So given this kind of subvolume, now we want to consider the 2D data, right? The 2D and 3D, the camera trajectories that we had. So in ScanNet, the camera parameters are known. The extrinsics, which is the locations of the cameras within the scene, have been estimated. So we have that, and the camera intrinsics, so which is things like the focal length of the camera are also known, which means that we have the relation between the 3D space and the camera's 2D space. Right. So using this, once we select a certain set of voxels in the scene, we can project those voxels 3D locations onto 2D space and then see for a given camera, that is. So we pick a subvolume, a set of voxels, and then we pick a certain camera pose. We project these voxel locations to the camera space and then see how many of these voxels actually land into this 2D space. So this gives us a mapping between the voxels and pixels. So again, considering a subvolume like this would give us something like this. So here what we're doing is, this is the 3D subvolume that we considered, and we have many cameras, camera positions in the trajectory, right? And many of these cameras need not necessarily be looking at this subvolume. They could be pointed somewhere else, right? So we compute the coverage of the subvolume, which is how many voxels in the subvolume are actually seen by a particular camera, and then pick the top five camera positions that are actually looking at this sub volume of voxels. Right. So this is done again in the same way as is done in 3D MV. We do a greedy incremental picking of the camera positions to maximize the coverage of the subvolume, such that every new camera pose that is added it, increases the coverage as much as possible. So in that nature, in that way, it's a greedy selection of camera poses. So once we have a set of subvolumes like this, and for each of them we have corresponding set of, say, camera poses which are covering these voxels here. So then we are ready to integrate, say, the 2D information with the 3D one. So we'll see what these kind of correspondences actually look like. So this is the RGB image taken from a pose, a certain camera pose, and this is the 3D mesh that we started out with. So here, this is actually the voxel grid that we have computed from the mesh, and the red region is the part of the voxel grid that we are actually considering, right? So we can see that we are only mapping pixels within this subvolume. And the other thing is that we can see the voxels are much bigger than the pixels that we have here. So here every individual point is 1 pixel, whereas here this bigger region is 1 voxel. So there could be multiple pixels that are mapping to 1 voxel and the other way around. So when we consider 1 voxel, it could be multiple pixels that are mapping to that. But to keep things simple, we'll just consider a 1:1 mapping for now. And the same example shown a little differently. So this is the original mesh, and these are the pixels here mapping to certain surface voxels here, right? So we have to be sure that we are only considering the surface voxels here because we don't want it's not possible for a pixel in the image to map to a 3D location which is actually inside or not seen in that view. So again, another example. So here we can see, for example, something that is actually covered in the RGB image need not necessarily be present in the mesh reconstruction. So another example here of the same thing. So the other thing to note is that in this one, so the selected 3D region could only be a part of the 2D. So the choice of getting a good coverage is quite important here. But it's also not very easy because the number of camera poses in the data set is very large, right? The trajectory, it's recorded as a video. So we continuously have a large set of camera poses, and then it's computationally not feasible to check for every single pose if it overlaps with every single volume. So just by the nature of how we do this, it's possible to miss out on some camera poses that could give us better coverage of a certain volume. So once we do this, we end up with something like this in 3D. So the blue voxels are the ones that are occupied within a certain the subvolume, and the red ones are a subset of those voxels which are seen from the nearest camera pose. So on average, within the sub volume, which is a 32-64 grid, we have only about 2,000 voxels which are occupied. So like I said, when we're doing 3D segmentation, it's mostly free space, right? So this voxel grids are actually not the best representation of free space, but we chose to go with this initially. And then only about half of these are going to be covered by 2D, which means this is not optimal, that we are not actually using all the 2D information. So we'll see what happens with this once we do this in the 3D MV way. So again, this is an explanation of what 3D MV is actually doing with the 2D images. So this is the 3D fully convolutional architecture that I mentioned earlier, the same thing. So for each subvolume here, we obtain the nearest RGB image, nearest based on the coverage. So we take this image and then pass it through a pre-trained convolution network, which is trained for 2D segmentation. Since we have the 2D segmentation labels as well in ScanNet, and we obtain some intermediate features here. So these features are then what is known as back projection is done on these 2D features, which is just the inverse operation of projecting from 3D space to 2D space, which is a common operation in 3D geometry. So since we know the depth images here from the say Kinect sensor or some other sensor, we can project the 2D locations back into 3D to get a 3D volume corresponding to these 2D features. And based on the mapping that we got earlier, we are only going to keep the features that fall into this subvolume. So once we have this volume is can be treated identically to the other one that we had originally in 3D. So these two, so we have a similar network here, which is going to downsample this and then give a smaller 3D volume. These two are concatenated as additional channels and then upsampled again to get label predictions on the whole volume. So this is the original 3D MV method that I've described here. And this was shown to give a very good improvement on using 3D alone, especially on objects that would be better seen from images. So such as smaller objects which don't have a very clear structure when you look at it in 3D. So say something like flat objects, say like a television or something that is flat on the wall, right? So these things that are not very clear in using voxel grids alone would become more clear when using 2D features. So till now, this was mostly a re-implementation of 3D MV. And then the next step is our main motivation, which is how can we combine contrastive learning along with fusion of 2D features. So contrastive learning has been done within single modalities earlier, which is within 3D itself or only 2D, contrasting different positives and negatives between samples. So what exactly happens here is we have pairs of 2D only or 3D inputs, and then positives are known to have similar features for some reason, and usually this is done by augmenting one sample, getting another sample through standard say data augmentation methods, and then we know that the corresponding locations between these two are expected to have similar features, right? Because they are originally the same sample. And then negatives could be obtained in different ways. Say, for example, negative mining or anything other than positive could be assumed to be a negative. So we do this, and then this is one simple method to get positives and negatives. And this can be done completely in an unsupervised manner. So we don't need to annotate samples that are positives and negatives. So in our case, this would look something like this. Say between 2D and 3D, we already have the mapping between these two spaces, and we can consider a 2D location here, say on the floor, and then its corresponding voxel here to be a positive pair, and so on. Right. So every mapping that we had earlier now becomes a positive pair between 2D and 3D, and every negative pair anything other than a positive becomes a negative pair. So this is the standard noise contrastive estimation formulation of contrastive learning. So we have some features on the 3D locations and some features on the 2D locations. And then we want to optimize these features such that this overall loss is reduced, right? So this we take the similarity between 3D and 2D features for positives, and we want this to be as high as possible, the similarity. And then for positives, and this is done in a softmax kind of formulation where everything else, this is normalized with respect to all the other pairs. So one of the existing works which has already done this is known as learning from 2D. So here what they do is they have a single view point cloud which is obtained using the depth images from ScanNet, and then the RGB images, and they obtain the similar mappings here. So the main difference from our work is that they use a single view point cloud, whereas ours is we are using a multi-view representation of the scene. I'll just come back in a minute, 1 second. Is it okay?
Yes, Chandan.
Yeah, just 1 second. Yeah, sorry. So, okay, we continue. So in this learning from 2D paper, the main difference was that they used a single view point cloud, and the data is not originally a point cloud to start out with. So these locations have no relation to the 3D reconstruction of the scene. Right? So how do we use the mesh itself to do this? So we follow mostly the 3D MV kind of approach here, and we keep the architecture mostly the same as it is. But what we add is a pre-training phase here, where we contrast the 2D features with the 3D ones that are output from the whole 3D MV network using the NCE loss. So this is done in a pre-training phase where we keep the 2D segmentation network fixed, right? So this has already been trained on the 2D labels. And then after the pre-training phase for the downstream task, which in our case is semantic segmentation, we do this as usual with the cross entropy loss. So some details about the data set and how we evaluate. We do all the experiments on ScanNet, and for training, we sample random subvolumes in the scene. This is a setting that has been recently introduced, which is called as the limited reconstruction setting. There is also the limited annotation setting, which is not relevant for us here. So limited reconstructions proposes 4 splits of data, which is 1, 5, 10%, and 20%. So we do the experiments on 1, 5, and 10% splits, as well as the full data set. And then in 2D as well, we can use either the full 2D data or only the limited reconstructions, the LR split of the 2D data. So we do our experiments in these two settings. For validation to get predictions on the whole scene, we have to use all subvolumes. So this is not, the subvolumes are not sampled in a random manner. We evaluate based on a voxel level labeling, which is slightly different from the ScanNet way, which is where the labeling is done on vertices, but the metrics are going to be comparable, and we stick with the same mean IOU metric. So for the 2D segmentation model, we have two choices. So this is ENet, which was what was originally used in 3D MV. And then we also tried out with a better 2D model, DeepLab V3, which is much more recent and also performs much better. And this is what, say, 2D segmentation looks like on a ScanNet image. So for baselines, we have two simple methods. One is back projecting the predictions of the 2D network. As we saw the back projection operation earlier, instead of back projecting the features, we can take the end predictions of the network and project those. Or we can project the ground truth 2D labels themselves to see how this compares with an actual learned method. So first, when we use the whole 2D data, we see that pre-training in the LR1 case has a huge improvement, right? So say if we are just using 1% of the scenes, the MIO is about 0.1. When we do contrastive pre-training, it's about 0.2, right? So for 1% of the scenes, which is about 12 scenes, this is quite a large improvement. But this gets smaller as we add more data. But in every case, we have some improvement over the baseline, which is with 2D features. This is the 3D MV essentially. We have some improvement when we do contrastive pre-training. And then we also see that we're using just 10% of the data, we can outperform the baseline, which is the 2D only projections back projected to 3D, or projecting the ground truth labels themselves. Right? So this is already quite a good improvement without using the whole data set. The next comparison that we want to do is using a better 2D model versus ENet. So we can see this is consistently going to improve downstream performance in every case. Right, so the improvement is usually most marked in the LR1 case, and this keeps improving in the other two settings as well. And more importantly, if we have a better 2D model to start off with, this is going to improve the 3D performance as well. So that means that we can make use of all the tricks that we know in 2D segmentation and all the architectures, which there are many more, and then apply them here to easily get better performance in 3D. The other question is, how do we train the 2D model itself? Do we start with a pre-trained model and then just keep it as it is? Or is there something that can be improved here? So these are some ablations that we tried out. So this is keeping the 2D model fixed, the 2D segmentation model, or we can train, say, only the last layer to adapt the 2D features better to 3D, and then do this at different degrees. So we could start with a pre-trained model and then train the whole 2D model as well while we're doing contrastive pre-training. Or we could start from scratch in 2D and then have additional 2D supervision, or we could just do the fusion. So we see that keeping the 2D pre-trained 2D model as it is without doing any additional fine-tuning while training with 3D happens to have the best performance here. So we think that this is possibly because it's hard to learn a joint space of 2D and 3D features, and it's much easier to have one of them fixed and then learn the 3D features. So another interesting question is, do we really need 2D information? If we know that it improves when we do, so we have seen from 3D MV that fusing 2D features to the 3D locations is going to improve this. But we could also just do pre-training and then use the pre-training just with a 3D only model. So not actually needing 2D the fusion of features, and just use the contrastive pre-training as an initialization of the 3D network. So here we see that if we do only pre-training, this is better only in the LR1 case. But if we do fusion and pre-training, this is the best result that we get in all cases. So this tells us that doing pre-training and fusing the 2D features with 3D have complementary effects. So doing either one of them is going to improve over the baseline, but doing both of them is always going to be the best. So this is the second setting that I mentioned, which is using only the corresponding fraction of the 2D labels. Right? So when we do this, we see that the performance is actually not much worse than what we got when we used the full 2D labels, right? So this means that it's okay to, because even either annotating in 3D or 2D on such a large scale is not very feasible always. So this is good for us that we can only annotate a small number of either 2D or 3D and then still get good performance improvements. And the other interesting thing is that this actually works even when we do this with the whole of the 3D and 2D data, right? So, which is not what we would expect. So normally this doesn't work. If so, the improvements are much easier to get in the limited data setting, but much harder when we are actually using full 3D supervision, because the 3D already happens to have most of the information that we want, especially since we are already fusing the features here. Another thing that is an extension of what was done in 3D MV is using multiple views. So we computed the top 5 cameras that were covering every subvolume, but the previous results were all with a single view. So does it actually help if we use more than one view, because we are adding more coverage of the scene every time we add a new camera? So as was done there, we experiment with 1, 3, and 5 views, and we see that we do consistently get an improvement here. But so there is this is harder to do because we are only sampling 1 in every 10 camera poses from the trajectory, where it would be quite computationally not feasible to pick every camera pose and then compute the back projection. But we do see an improvement here, and usually the improvement is initially larger, and then every additional camera doesn't add too much coverage, so we don't get too much improvement here. These are some qualitative results on the limited reconstruction setting. So this is with trained on 1% of the data. We noticed that the performance does improve on some smaller object classes, say like the TV, and the segmentation generally becomes a little more consistent, considering that 1% of the whole scanner data is very less. So we can qualitatively see this as well. But unlike the case of 3D MV, where it was much more clear what was happening, that augmenting the 2D features was mostly improving performance for objects that are better seen in 2D. Here it's not very clear, and the improvement in metrics is more spread across different classes, which is the effect that we get from contrastive pretraining. So, like I said, the effect is more complementary, and it's not identical to what we would get just by fusing features from 2D with 3D. These are some more examples on, say, 10% of the data, and see here we can see that as we increase from 1% to 10%, it's getting much better. So I'll wrap up with some directions for future work that we can think of. So here we are contrasting only at one level. So we are picking a certain resolution of the 2D images and the 3D voxels, and then contrasting there. And this happens to be some downsampled version of the original volume itself. Right? So it would be better to contrast at different levels and actually get this working and have an appropriate architecture for this. The other thing that can be done is using multiple camera views without pooling the information and not losing the information that is there in each of them. Right? So the method that we have employed here is just doing a max pooling over all the views, which is invariant to the number of views, but then we are losing the individual information from each of them. Another thing that could be interesting is doing joint training with both the losses in a single stage, which is practically it becomes a little easier to do this, and it could have some improved effects here when we train both the losses together. And then finally, instead of just using cross-modal positives and negatives, we could also have pairs within 3D and 3D as well as 2D and 2D. But then how to actually put this into the training phase, where so we would probably get this using some kind of data augmentation where the samples are not corresponding to each other anymore, right? But when we are actually training the current architecture, we need the samples to be associated with each other in the same locations. So this would no longer hold if we did augmentation within one of the modalities. So how to use this as well is an open question. So I'd like to conclude by with a few points. So we saw that using contrastive pretraining improved our downstream IOU on semantic segmentation between 75% on the 1% setting up to say 5% on the 10% of data setting. And we saw that pre-training is going to be complementary to the fusion of 2D features. So this is a useful add-on in addition to any methods that are already fusing 3D and 2D features. And importantly, it is now possible to improve the 2D network separately from the 3D architecture itself. Whereas because in 3D we have different kinds of constraints, whereas in 2D it's a little simpler to actually optimize the networks and then try out different things. And there is already so much literature which deals with 2D segmentation. So any improvements here can be more directly applied into the 3D space. Yeah, so with that, I'd like to conclude and then thank you for your time, and we'll be happy to take any questions. The code for this is on GitHub, and I'll also be happy to get in touch by email if anyone is interested.
Yeah, thank you so much, Chandan, for the wonderful talk. And it's really an interesting area of research to fuse 2D and 3D information. And it's quite nice talk. So whosoever are watching in the Zoom, if you have any question, please raise your hand using the reaction button. And then in the order, I can go one by one. And whosoever watching in YouTube, please use the live chat option if you have any question. Okay, so it seems in the Zoom, no one is having questions. So I have a question, Chandan. So how do you, maybe I missed this portion. How do you actually align the 2D images and some portion of the 3D? Like you have to render and then you have to align them. How do you align them actually? If you can elaborate.
So I think this is mostly dealing with what the ScanNet actually has, right? So the ScanNet is originally RGB and depth, and then you have the mesh. But what is not shown here is that you have the camera poses, which is telling us where the yeah, right. So we know where the camera is, and then we have the depth images as well. So if so, you can imagine the 2D image being right in front of one of these cameras here, and then you have the depth image as well. So if you project every pixel of the the depth and RGB are essentially in the same space. So apart from the calibration of the rig, right? So which is something that can be handled like in a stereo camera. So you can project the 2D locations back to 3D, which is what the back projection operation is doing.
Yeah, yeah, I understand that. By the way, do you also do some camera position interpolation or something like that? Because I believe the camera positions are restricted to for certain places, and there may be certain places where camera is not there. So do you do some kind of camera position interpolation or something like that?
Yeah, that's a good question. So that is something that has been done in a later work called the virtual multi-view fusion, I think. So that one is, I mean, that's a really nice paper where they sample different camera views and then render the mesh from these views. I think so. They render the mesh and render the 2D labels
Mhm.
to get new labels, and then but that method is completely doing it in the 2D space where they are training a 2D model
I
to do
see.
to actually render the mesh from new views. You would have to do some kind of novel view synthesis to actually use the RGB images, because the mesh itself, if you see, it almost looks nothing like the images that you have, right? If the image is much clearer than the mesh that you get here. So if you simply pick new camera poses here and then rendered them, the RGB images from that would not be very useful. But
Okay.
we're not doing anything like that here. We are only considering the positions which are actually there in the data set.
I see. I see.
But
Anyway. Mhm.
it would be
Yeah.
interesting to do something like virtual it's called virtual multi-view fusion. I think something like that would be quite interesting.
Yeah. That's quite interesting, and maybe some of our audience also can be interested in and contact you on those kind of research direction. And once again, I'm asking whoever is listening over here. I think Saket is having some question. Please unmute yourself and go ahead.
Yeah, so my question is, when you're training with the contrastive learning, so is there any way of how you're preventing any naive solutions?
Naive as in your 3D and 2D becoming equal, something like that, right? The features.
Yes.
I think so. I think in practice, if nothing like that actually happened. Let's see. We're not particularly doing anything to prevent this from happening.
I mean, for example, if you look at like other popular ones, usually they have an additional projection layer or something which brings in the difference. Or they have like a momentum to bring in this difference between like a target encoder and a whatever you're moving encoder, right? So is there any difference brought between the networks, or you didn't face it?
I didn't have any trouble like this. So the thing is, we maybe I'm not sure of the work that you're referring to. So here we keep one of them fixed, right? So one of the features is going to be fixed, and only one of them is changing.
Okay.
And is there anything that would prevent that from exactly? So the other thing is that we have I mean, only in the pre-training phase it is possible. But the other thing, we also don't have supervision over. We don't. All the locations are not mapped between 2D and 3D, right? Just because of the way that we are doing the projection. So due to that, not all.
Okay, another thing. I think this is something which I may have overlooked. You said you have a positive and a negative sampling, right? And this is for the technique which I'm speaking of, right? Where you get positive and negative samples. Okay, so that itself actually will bring in the difference for you.
Okay.
You don't need a projection layer or anything. Yeah, when you are sampling positively and negatively, that's one way to not get the negative.
You mean, okay, so you mean so yeah, correct. You're right. The negatives will, because we want the negatives to have different features, right?
Yeah.
Correct. So
And how do you do? And here, negative sampling is easy, right? I mean, you just have to not get the points which are not in the neighborhood that you consider.
Exactly. It's so like you said, something like a neighborhood would actually use the available information better. But here we are just considering a 1:1 mapping. So everything that is not mapped becomes a negative. This is it's quite a simple way of doing this. There are better ways of choosing negatives and so on. So yeah, it could be something that is not in a neighborhood.
Yeah, got it.
Thanks.
Okay, so I guess Henak has some question. Henak, please go ahead, unmute yourself and ask. Oh, I see Henak is having some internet issue. So he sent me the question and I'm asking his question on behalf of Henak. So his question is, if someone to to follow your research path, what would you advise them?
I didn't completely get. So, follow the research path as in?
Yeah, I mean, as far as I get, like Henak is quite interested probably and inspired from your research, and his question is like the way you started and you came up to this thing, and so if someone makes you as their research idol, so how they should start and how they follow your kind of path. Probably that's the question.
Yeah, I mean, I'm just a beginner, so it is. I think depending on what stage you're in of doing things like this, machine learning, deep learning, or computer vision. I guess if you're a student, it would help to take some relevant courses in 3D geometry. The actual deep learning part of it is something which is that can be picked up, but I think having strong fundamentals in 3D geometry and 2D computer vision as well really helps. Which is not something that I had at that time, I think. And then I think later working on some actual hands-on projects and then re-implementing a paper from scratch is a huge step up in terms of what you learn and what you can be capable of. So, for example, this is my master's thesis. So a lot of the time actually went into re-implementing the 3D MV paper and then learning about preparing the data correctly and such things, which took a lot of time. I think doing one proper re-implementation of a paper is a really good experience. Along with, so end to end, without actually reusing anything that is already there, so code, data sets, and so on, and then trying to reproduce the results that are in the paper end to end, right? So you're getting the visualizations and then the same metrics that are there. That is a very good step, I think, in doing something like this, which gives you knowledge of this at all levels.
Yeah, exactly. I completely agree with Chandan, and it is the way to research actually. So you have to learn it by doing it. So Henak, hopefully you got your answer. If anyone else is having any answer, please raise your hand and unmute yourself and ask him. Okay, so I don't see any raising hands. If anyone's still having some question, don't feel shy. I'll just give it a minute and then we should be fine and to call it a day and proceed with our other plans.
I think we're right.
And anyway, once again, thanks to Chandan for this great talk and for supporting us. We started this Amygdala AI. So please, guys, if you liked his talk and his research, please contact him in his email ID. It's there in the bottom of the slide, as you can see. And hopefully we'll have some good research collaboration with Chandan in future. And yeah, Chandan, do you have any advice or any general comment about the audience?
Yeah, I mean, first of all, thank you so much for the opportunity. It looks like a very good initiative, Amygdala. So it was, I'm very happy to be part of the first few sessions. Yeah, I think general advice, it would be nice to get in touch with people and then talk to them. But other than that, like what I said, I think that, so, like I said, I'm also just starting out in this, I feel. So.
Yeah, I see. Okay, so someone is asking if the slides is shareable or something, but I think we are already in the YouTube, so I think we don't need to share the slide additionally. I guess you can always refer back to the YouTube videos, and we are not going to delete the videos anyway. So anyway, well, I'll stop the live on YouTube, and it's a nice session for all of us, and thanks to Chandan once again. And we'll hopefully see all of you again in our next Amygdala talk, maybe in